Welcome to The Explainer. Today, we're going to crack the code on circuit theory. We're taking the complex rules that literally power our modern world and breaking them down so they make perfect sense.
Okay, let's dive right in. Take a look at this. Yeah, I know. This formula for a magnetic field, it looks incredibly intimidating, right? But stick with me. By the end of this explainer, you're not just going to be staring at a bunch of symbols. You'll actually get the core ideas of current, force, and fields that bring an equation like this to life.
First things first, we need to get a handle on the basic rules of the road for electricity. Think of these as the fundamental laws that tell us how current behaves, everywhere, from your smartphone to the entire power grid.
So our journey starts with this, just beautifully simple rule, Kirchhoff's first law. The easiest way to picture it, think of traffic at an intersection. The number of cars going in has to equal the number of cars coming out, right? Well, it's exactly the same with electricity. All the current that flows into a point must also flow out. It's this elegant, perfect law of conservation. Nothing gets lost.
Okay, so how do we actually use that rule? Let's walk through it. It's kind of like solving a puzzle. First, you got to find the main intersection, which we're calling V. Then you apply the law. Current in equals current out. After that, we just define each of those currents using what we know about voltage and resistance. Then, a little bit of quick algebra, and boom, we get the voltage at that key point. And once you have that, you can find the final piece of the puzzle, the exact current we were looking for.
And there it is, the answer. After all those steps, you get a single, precise number, 0.6 amps. I mean, this is the real magic, right? We took this abstract rule about traffic flow and used it to predict the behavior of something totally invisible with perfect accuracy. That's the power of these principles.
All right, so we've got the rules of the road down. Now let's pop the hood and look at the building blocks, the actual parts engineers use to control all that electricity. One of the most crucial concepts here is time. This simple formula gives us what's called the time constant. You just multiply resistance R by capacitance C. And this little number, called tau, basically tells you the circuit's reaction time. Like, how fast can it charge up? How quickly can it drain? That's what it's all about.
And this is where things get really interesting, because different parts have their own, let's call them personalities. If you line up resistors one after another in series, they just add up. Simple. But capacitors, no. They play by a totally different set of rules. It's this more complex thing with reciprocals, and honestly, mastering these differences, that's what being an engineer is all about.
Okay, so we've got our current, we've got our components. But here's the thing. Electricity never, ever works alone. It's got this inseparable partner, a force that it both creates and is influenced by, magnetism.
And to really get this connection, there's this awesome, super simple physical trick. Ampere's right-hand rule. Just point your thumb along a wire in the direction of the current and watch how your fingers naturally curl around it. That's it. That curl shows you the direction of the magnetic field. It makes this invisible force suddenly tangible. So, where does that magnetic field even come from? Well, the answer's right here in this formula for magnetomotive force, which is basically the magnetic push. You want a stronger magnetic push? You just add more turns of wire, or you pump more current through it. It really is as simple as that. But you know how it goes, right? For every push, there's always some kind of pushback. For magnetism, we call that reluctance. You can just think of it as magnetic friction. It's all about the ratio between that push and the magnetic flow you actually get. It's this constant dance, this push and pull, that defines any magnetic system.
And check this out. This is my favorite part. The units themselves tell you the whole story. The unit for this magnetic resistance is ampere turns per Weber. Okay, ampere turns is the push. Weber is the unit for the magnetic flow. So the unit is literally asking the question, how much push does it take to get 1 unit of flow? The answer is baked right into the name.
Okay, we've covered the rules, the building blocks, and these invisible forces. So, what's the point? How do we take all this theory and actually build the tech that powers our world?
Well, it all starts at the tiniest, most microscopic level, with materials like this, the N-type semiconductor. By adding a specific impurity, what's called a donor atom, we basically create a surplus of free-moving electrons. And these aren't just any electrons, they're like little workers just ready to carry information and power. And now,
This is where the real magic happens. When you join that N-type material with its opposite, a P-type material, you create a PN junction diode. Its main job is something called rectification, which is really just a fancy way of saying it's a one-way gate for electricity. Current can go one way, but it can't go back. And that simple little gate, it's the foundation of pretty much all modern electronics. It's a huge deal.
And what's amazing is how these principles scale up. I mean, think about measuring the power for an entire factory, a huge three-phase electrical system. How on earth would you even do that? Well, the answer is surprisingly simple. It's almost beautiful. Engineers use 2 meters, and the total power, it's just the reading from one plus the reading from the other. That's it. All that insane complexity boiled down to simple addition.
So think about where we started. We had that intimidating formula, and now we're here, with these elegant rules that are basically conducting this entire symphony of electricity. We saw current acting like traffic, magnetism and electricity doing their dance, these tiny little silicon gates standing guard. So the next time you flip a switch, just take a second. Picture that whole hidden world springing to life, all those invisible laws all at work just for you. What kind of symphony will you hear? Thanks for cracking the code with us on The Explainer.